Students, hi, this is Mr. Bob. In this video, we're going to talk about particle physics, part 1, which is subtopic 7.3. And before watching this video, you should either print out a copy of page 8 of your data booklet, which has that subtopic 7.3 info, because you're going to likely want to mark it up. Or you could, if you wanted to use a Google slide, I've given you a link there, bit.ly/particle physics data booklet. If you type that into your computer, you should get a Google slide of that nature. You can make a copy of it and mark up that Google slide. Also, you want to set up focus notes in your journal or do it on a digital template. And I've given you this template before, but just to put it here again, bit.ly/fn template. And about a week later, I would suggest you think about reading section 7.3 of the Oxford IB Physics textbook. I'll put a link to that on the Canvas course. And then as always, revisiting your notes in a way that makes your brain struggle or think about them actively. Okay, and then again, as always, avoid just mindlessly copying, stop and rewind the video as needed. Just actively listen and selectively write things that are emphasized by me. Sample problems, I would definitely urge you to pause the video and work it as far as you can by yourself. And if you're still confused, make sure you point out or identify those points of confusion and take some action about them. Essential question for these two videos: what is the standard model and what are the main components of the standard model? So when we talk about the standard model, what we're talking about is a sort of model / theory that physicists have composed of or have come up with, say, since the late 60s, early 70s, and they've added to it and they keep adding to it and refining it, that explains the most fundamental explanation of what we think is happening with matter, the stuff that we can detect with sensors, so to speak. Okay, and there are three major divisions in these elementary particles. And again, if you go back to like chemistry or other science classes, you probably learned that at some point in the past, we thought the atom was the smallest possible divisible particle. And then we learned, no, an atom was comprised of protons and neutrons and electrons. Well, in fact, we've learned since then that there's even smaller pieces, components, and additional pieces of components. And that's what the standard model tries to explain. What are the pieces, components, and how do they interact with each other? So the three major divisions are force carriers, quarks, and leptons. So the force carriers are the particles that allow compatible particles to sense and react to each other. And they sense and react to each other by emitting some sort of force on one another, okay? And what we believe now, and I'll talk about this more in a slide a little later on, is that what we believe now is these particles, when we say they're experiencing a force, they're actually exchanging these other particles, which are called these force carriers. Another word for the force carriers is you'll often hear used as the word gauge bosons. One example of a gauge boson is a photon. Okay, photon, a packet of energy in the form of a light wave. That is one example of a force carrier. Quarks is the second main classification, and they're heavier, they're more tightly bound, and they're the ones that make up the protons and the neutrons that are in the nucleus of an atom. And then finally, we have leptons, which are lighter, more loosely bound particles. The most common one you're familiar with is the electron, but there are other ones that we'll talk about. So there we have force carriers, quarks, and leptons. Now, right away, I just want to make sure we understand what's going on here. Force carriers are in red, so let me use red. Okay, and you should be marking this up. The force carrier information provided is down here. So these are force carriers. Okay, and then what do we say? The quarks are in blue. Okay, so in blue, I'm just going to highlight the section of information that your data booklet has about quarks. And that's right here. And then finally, the leptons, we used green. So let's use green as well. Leptons over here. This is the information about leptons. And even though this looks very unfamiliar to you by now, or right now, within a couple of weeks, you're going to be like, oh, this makes so much sense. So it's really important. I just want to emphasize, it's really important that you are intimately aware of what is in your data booklet on page 8. And this is why I suggested to you that you have this and you mark this up and you refer to it frequently, because it'll help you so much in this unit. Let's talk a little bit more about the force carriers, because the force carriers, there are basically four fundamental forces and there's a force carrier associated with each, okay? So let's talk through them. And we're gonna go from most powerful to weakest, okay? So the first fundamental force is something we call the strong force. You'll also hear it called the strong nuclear force. And the force carrier associated with it is something called a gluon. No, I did not make that up, okay? It's the strongest of all the interactions between the particles. And just for a comparative nature, we're gonna assign that an arbitrary value of 1, and we're gonna compare the other fundamental forces to the strong force to get a sense of the magnitude of difference here. Okay, so the second one, the second fundamental force we want to make sure we understand is the electromagnetic force. And the force carrier for that, I already mentioned, is the photon. And so by comparison, if the strong nuclear force has a value of 1, the electromagnetic force has a value that's 1/100th of what the strong force is, or 10 to the negative 2. So it's significantly less powerful than the strong force. Let's keep going. The third sort of fundamental force that physicists have been able to identify with their work so far is something called the weak force. You'll also sometimes hear it called the weak nuclear force. And you can see there are 3 force carriers for that one: the W plus particle, the W minus particle, and the zeta neutral particle, okay? And this interaction has a relative strength of 1/1,000,000th of the strong force, 10 to the negative 6. And then finally, the fourth fundamental force is gravity, the gravitational force, which you're intimately familiar with. And the exchange particle for that is what we call a graviton. Now, the interesting thing is, if you had to take a guess, how powerful do you think gravity is? How strong do you think gravity is compared to the interaction, the strong force being 1? Pause this video, make a prediction. Here it is. It's 10 to the negative 39. That is 0.0 with 38 zeros and then a 1. Here, I'll show you. Looks like that, okay? Gravity is extremely weak in comparison to the strong force, which is a really fascinating idea. Okay, so you should be able to list the 4 fundamental forces, and you should be able to list them in order from strongest to weakest or weakest to strongest. Okay, so there's a Japanese physicist in the 1930s who came up with this idea that I've already started talking about, which is this theory that when we said something is acting on another object, exerting a force on another object, what's really happening at a fundamental level is that these particles are exchanging force carriers. So, like I said, all forces are due to the exchange of particles between the elementary particles. So here's a simple example. If I have 2 protons in space, you can see them there. What Yukawa basically said is, the reason these 2 protons repel each other, the electromagnetic force, positive charge repels. What they're really doing actually is they're exchanging. Did you see that? They're exchanging photons. And it's that exchange of photons that represents or that causes the force that we measure. Okay? So the photon exchange is the electromagnetic force in particle physics. So Yukawa also went on to say, there are some forces that have a really long range. For example, electromagnetic force is got an infinite range because the photons live forever. Those exchange particles are long-lived, and so they live forever. But there are other force carriers that have a very short life. They have a very short range, okay? And one of them is the gluon. We know that the gluon, for example, has a very short range, somewhere around 10 to the negative 15th meters is how far it can travel. And so it also has a very short life. And so there's a photon that goes forever and ever, but that's the long range exchange particle there. But then if we have a gluon, the gluon doesn't make it very far. This is what we call a short range exchange particle, or an important word is a virtual particle, okay? So some force carriers are virtual particles, other force carriers are not. The ones that are virtual have a very short range, very short life. The ones that have long range are not considered virtual, okay? So if you look down here, The gluon and the photon, these are what we call long range, because gravity, excuse me, that I totally said that wrong. It's not the gluon, it's the graviton and the photon. These are long range, okay? They have effectively an infinite range. Think about it, the sun travels, the gravitons from the sun basically keep the earth orbiting around it, right? And then these short range or the virtual particles are these guys right here, virtual, the gluons and the ones that are associated with the weak force. Boom, boom. Okay, and I think, yes, I'm just, this slide just basically says what I just told you the last thing. So the virtual particles are the ones that are in orange there. The strong interaction force, which is the gluon, and the three particles associated with the weak force. Okay, let's talk about quarks. So quarks, what's going on here? A little bit of history to help you understand how we came up with this thing that's going to sound really bizarre at first. Well, if you look, what started happening is in experimental physics, we started building these particle accelerators. And what they were is they were these really complex devices that would accelerate what we thought were the most fundamental particles at the time, things like protons and neutrons. And they would accelerate them and they would smash them into each other. And then we would have detectors all around to detect what happened when you smash them. And out of having these high energy collisions, we discovered that there were other particles that were being revealed for brief moments of a second, but nonetheless, consistently, collision after collision, we were seeing trends that were undeniable. But by the mid 1960s, we had like this alphabet soup of particles. Like sometimes we were seeing lambda particles and charmed lambda and bottom lambda and sigma. And you can see physicists just kept having to come up with more names because just more and more particles were appearing. And it just seemed like there was no rhyme or reason as to why certain particles were appearing and others weren't. So some physicists basically looked at all this information and tried to come up with some sort of underlying framework that would explain why we saw certain particles and not others, and why particles had certain characteristics in terms of charge and other behaviors. So two scientists were Gell-Mann and Zweig. They proposed a model where basically they identified and they came up with this idea that let's call a subparticle a quark. And there are certain quarks, different types of quarks that combine in different ways to create, for example, a proton. And there's a different combination of quarks that create the neutron. And then an equally different combination of quarks creates the lambda particle, et cetera, et cetera. And by doing this, by mixing and matching these different quarks, you could, in effect, explain all of the experimental observations that had been occurring up until then. Okay, their original proposal had 3 quarks. Since then, since the decades that have followed, we've done more and more experiments, built bigger and stronger particle accelerators, and basically we've come up with what's right now our understanding, which is we have 6 quarks. And here's a little more history. In '68, Stanford Linear Accelerator provides evidence that a proton has constituents to it. So a proton has pieces, parts to it. And that's when the up and the down quark was identified. And in the '70s, we get the charm quark and the bottom quark. And again, these things were first thought about and believed to be existing. Theoretical physicists believed that this was the case. And it took decades, sometimes 10, 12, 20 years, in some cases 30 years, for experimental evidence to come to basically support this theory. But the experimental evidence has come. And honestly, the one thing I want to tell you about the Standard Model is the more experiments we have done, the stronger the evidence that supports it, okay? So like all sort of theories, we continue to test it, we continue to explore it and probe the limits of it. But so far, the Standard Model has been one of the most durable and one of the most impressive theories in physics. And so this is where things stand today in terms of our understanding of the number of quarks. We have 6 quarks, and you could think of them in pairs, the up and the down, charm and strange, top and bottom. Okay, this doesn't mean that we won't discover more quarks in the future, but one other thing I just want to point out, why were the up and down discovered first? I want you to look at these mass figures, because these mass figures really reveal, in order for these quarks to appear momentarily, we have to have a strong enough collision, an energetic enough collision, that they might briefly show their appearance. And so notice the reason up and down came first is because they're the lowest energy, lowest mass ones, right? Remember mass and energy, the equivalence there. Notice that the strange quark and the charm quark, a little more massive, top and bottom, a lot more massive, okay? So top and bottom took longer because you had to build a more massive particle accelerator and collider in order to be able to make observations of it. Okay, let's talk about the vocabulary. It's going to be really important that you understand the vocabulary that goes along with particle physics. So a hadron is a particle that participates in the strong force. So for example, a proton is an example of a hadron because it participates in the strong force. A neutron is another example, okay? But we can say more broadly, because there's a larger list of particles other than just protons and neutrons that participate in the strong force. So a baryon is made up of 3 quarks, okay? And by the way, that's how quarks actually look. Just kidding. An antibaryon, which we're going to talk about antiparticles in another video, but just so you know, an antibaryon is made up of 3 antiquarks, okay? And the way we just identify anti is we put a little bar up above. And you should already know this, right? Because when we talked about beta to K, remember we talked about a neutrino, and we also then talked about in some cases you get the antineutrino, okay? So this is the same nomenclature. When you have a bar on top, it's the antiparticle. And again, we're going to talk more about antiparticles later. Also next time, we're going to talk not only talk about antiquarks, but also uncle quarks. Haha, get it? Okay, and then a meson is made up of a quark and an antiquark. So Q bar, okay? And when I say Q, I'm just saying that a generic quark, right? For example, a meson could be an up and an anti-down, or it could be a top and an anti-down, etc. Okay? Those are just 2 examples. Baryons and mesons are both examples of hadrons, okay? So again, a hadron is a particle that participates in the strong force. You may have heard of the Large Hadron Collider. Guess what? They are colliding hadrons, particles that participate in the strong force. A quick aside, what type of particle does an IKEA emit? A photon. Okay, let's talk about this practice problem. Protons and neutrons in terms of quarks. So a proton is a baryon, and I'm going to tell you this now, but you have to remember, this is one of the things IB would expect you to remember. Proton consists of 2 up quarks and 1 down quark. Also, you need to know that a neutron is a baryon that's made up out of 1 up quark and 2 down quarks, okay? And these are both hadrons. By the way, in the past, students have tried to figure out a mnemonic to remember this. And it's funny, this one caught on a few years ago. It's really inventive. You just say pood nud. But honestly, for students 1 year, it really seemed to work. So that's your call. So this is where we kind of get to an interesting part. We know that a proton, you've known for the longest time, a proton is a +1 charge. Well, how does that work if it's made up of pieces, parts? Well, notice down here, the up, the charm, and the top quark each have a charge of positive 2/3 E. Remember, E is the fundamental charge. The down, strange, and bottom quark have a charge of negative 1/3 E. Okay, so let's see what happens. Let's see a proton. If we're going to show that the charge of a proton is 1, so a proton is equal to up, up, down. Well, we know 1 up is positive 2/3 E. We'd have to add that to the positive 2/3 E of the other up, and then we'd have to take away the 1/3 E from the down. So 2/3 and 2/3 is 4/3. Take away 1/3, and what do we get? We get +1 E. So that's the charge of a proton. Interesting. What about a neutron? A neutron we know as nud. So what do we have? +2/3 E, and then that one down is -1/3 E, and the other down is -1/3 E. What do we get? 2/3 minus 1/3 is 1/3, minus another third is we get 0 or neutral. So hopefully you're starting to see how, as crazy as it sounds, this whole model of quarks actually explains things we already knew, but maybe in a more fundamental way. And it also explains other phenomena that our previous theory couldn't explain. All right. All right. Let's finally talk about leptons. Leptons, remember we've talked about force carriers, we talked about quarks. Leptons, they interact via the electromagnetic force carrier, which is the photon. We already talked about that. So, and remember, the important thing is leptons do not interact in a strong force. In other words, the gluon doesn't do anything for them. Okay, so here you see are the 6 types of leptons. Now, I just want to make sure you understand that each vertical column here is considered its own generation of leptons. So what I mean by that is notice this column here, where you have the electron. This is the lepton you're most familiar with, probably maybe you're exclusively familiar with. But this electron and its accompanying neutrino, the electron neutrino, is considered a generation 1 lepton. And that's going to come into play later on when we talk about conservation laws. Generation 2 leptons include the muon and the muon neutrino. And then finally, generation 3 leptons include the tau and the tau neutrino. One interesting note about muons. Muons are created by cosmic rays in the upper atmosphere. Excuse me. They're created by cosmic rays, and then they tend to manifest themselves in the upper atmosphere. And the average lifespan of them is about 2 microseconds, which is an absolute eternity in particle physics, okay? So that's interesting. So hopefully you were able to now answer the 2 essential questions from this video. What is the standard model? And what are the main components of the standard model? Again, there are other videos that I'm going to be sharing with you that'll go further into these topics. I hope you've enjoyed this. Thank you.